Toss a fair coin twice. Now ask yourself, what are the chances of getting at least one head? Most people feel it's fairly likely, somewhere around 3/4, and that instinct is spot on. But where does a number like 3/4 come from? Quietly, your mind did three things. It listed every possibility. It picked the ones that count as success, and it assumed each was equally likely. Today, we make that reasoning precise. We'll build a language of sample spaces and events, lay down three axioms, and watch every rule of probability fall out of them. Start with the ground floor. The sample space, written capital S, is the set of every possible basic result of an experiment. Each single result inside it is called an outcome. Toss one coin, and the sample space is simply heads or tails. Two outcomes. Roll a die, and it grows to the numbers 1 through 6 outcomes. Toss a coin twice, and we track the ordered pair. Head head, head tail, tail tail. Four outcomes in all. And notice, one single element, like the number 4, is one outcome. The whole collection is the sample space. Keep those two apart. Now the key move. An event is nothing more than a subset of the sample space. Any collection of outcomes you care about. Here is the dice sample space. The 6 faces sitting inside S. Formally, E is an event. Whenever E is a subset of S, take the event even number. That's the subset 2, 4, 6. Let me shade those 3 faces green. An event can be a single outcome, several, or even none at all. The empty set is a perfectly good event. It just never happens. We call it the impossible event. Probability itself is a rule. Call it capital P, that hands every event a number. For any valid P, just 3 axioms must hold. Everything else is built on top of them. Axiom 1, non-negativity. Every event's probability is at least 0. There is no such thing as a negative chance. Axiom 2, normalization. The probability of the entire sample space is exactly 1. Something in S is certain to happen. Axiom 3, additivity. If two events are disjoint, they share no outcome, so their intersection is empty. Then the probability of A or B is just P of A plus P of B. Let's see axiom 3 in action. Roll a die and let A be the outcomes 1 and 2, and B be 5 and 6. A and B never overlap, no number is in both, so they're disjoint, and axiom 3 lets us simply add their probabilities to get the probability of A or B. P of A or B equals P of A plus P of B. Clean addition with nothing counted twice. To rules that follow directly, start with the empty event. Watch the axioms do real work. First, the impossible event. S and the empty set are disjoint, and their union is just S itself. So by axiom 3, P of S equals P of S plus P of the empty set. Subtract P of S from both sides, and the probability of the empty set must be 0. The impossible event carries probability 0, as it should. Now the complement rule, one you'll reach for constantly. Take any event A, drawn as this blue region inside S. Everything in S outside of A is its complement, AC. Together, A and its complement fill the whole space and never overlap. Since they're disjoint and cover S, axioms 3 and to give P of a plus P of AC equals 1. Rearrange and the complement rule appears. One more. The sanity check you'll lean on hardest. Every event A sits between the empty set and the full space. The empty set is inside A, and A is inside S. Bigger sets carry at least as much probability. That's called monotonicity. So P of the empty set is at most P of A, which is at most P of S. And we already know those two ends, 0 and 1. So every probability lies between 0 and 1 inclusive. Step outside that range, and you've made a mistake somewhere. Here's the catch. Axiom 3 only works for disjoint events. So what happens when two events can happen together? When they overlap. Picture two overlapping circles. Event A in blue, event B in green. They share a sliver in the middle. The outcomes in both A and B. The intersection. If we naively add P of A and P of B, that shared middle gets counted twice. Once from each circle. Watch it light up. The fix is simple. Add the two, then subtract the overlap exactly once to undo the double count. That's the inclusion-exclusion rule, the addition rule for probability. And it contains axiom 3 as a special case. If A and B are disjoint, the overlap is empty. That last term is 0, and we're back to plain addition. Let's put it all to work. A fair coin, tossed twice, with every outcome equally likely. The sample space has 4 outcomes, and each carries probability 1/4. Question 1. Exactly one head. That's the event head-tail or tail-head, 2 of the 4 outcomes. So its probability is 2 over 4, which is 1/2. Question 2. At least one head. Only telltale fails, so the event is the other 3/4. Exactly the instinct we opened with. Now let's verify it a second way, using the complement. The complement of at least one head is no heads at all, just tail with probability 1/4. 1 minus 3/4 is 1/4. The two agree perfectly. A tougher one, where overlap really bites. Draw one card from a standard 52 card deck. Let A be the card is a heart, and B, it's a king. 13 hearts out of 52 make 1/4. 4 kings make 1 over 13. And crucially, one single card, the king of hearts, is in both. So the intersection has probability 1 over 52. First, the chance it's a heart or a king. Straight from the addition rule. P of a plus P of B minus the overlap. Put everything over 52. 13 plus 4 minus 1 is 16. So 16 over 52, which tidies to 4 over 13. And a lovely cross-check by counting. 13 hearts plus 4 kings minus the one card we double counted is 16. Same 16 over 52. Now heart but not king. Split the hearts into two disjoint pieces. The hearts that are kings and the hearts that aren't. Their probabilities add up to P of A. So the piece we want is P of A minus the overlap. 13 over 52 minus 1 over 52. That leaves 12 over 52. The 12 hearts that aren't the king, which simplifies to 3 over 13. Your turn, and this one has a trap built in. Roll a fair die. Let A be an even number, and B be a number greater than 3. Find the probability of A or B. Pause here, and be careful about the overlap before you add. I'll wait. Here's the walkthrough. A has 3 outcomes. So does B, each is 1/2. But the trap is the overlap. 4 and 6 are both even and bigger than 3. That intersection is 2 over 6, or 1/3. So by the addition rule, 1/2 plus 1/2 minus 1/3. That's 3 plus 3 minus 2, all over 6, 4 over 6, which is 2/3. And check it by listing. A or B is 2, 4, 5, 6. 4 outcomes out of 6, 2/3. If you subtracted that overlap, you nailed it. Trap 1. Mixing up outcomes and events. You can only take unions of sets, not of bare numbers. Wrap outcomes in braces. The event 3, union the event 4. Trap 2, the most common of all, adding probabilities when events overlap. Plain addition is only legal for disjoint events. If they can happen together, subtract the intersection. Trap 3, using favorable over total blindly. That shortcut assumes every outcome is equally likely. The axioms never assume that a loaded die breaks it instantly. Trap 4, an answer outside 0 to 1. Any probability below 0 or above 1 violates the axioms outright. It's a guaranteed signal you slipped. Trap 5. Misreading complements. The opposite of at least one head is no heads at all. Every toss a tail, not exactly one tail. When in doubt, write the complement as a set. Let's lock it all in. An event is just a subset of the sample space. Sets are the whole language. Probability obeys three axioms. Every event is non-negative. The whole space has probability 1, and disjoint events add. That third axiom is your license to add, but only when the events share no outcome. From the axioms flows the complement rule. P of not A is 1 minus P of A, often the fastest route to an answer. And the addition rule handles any overlap. Add the two, then subtract the intersection once. Hold these 5 lines. Always ask whether events overlap, and probability will never trip you up.